My name is Jack Sanders, and I'm a graduate student in physics at the University of Michigan. Today, I want to talk to you a little bit about space and what we know about it. So, we know a lot of things about space, and almost all of them are because of light. When we look at these big, beautiful Hubble Space Telescope pictures, we see light from galaxies, going back almost to the beginning of the universe, and we've learned a lot of things with that. But light has some limitations. If you've ever been on a road in the fog, and you try and find the headlights of other cars, it's very hard to see. In the same way, there's dust in the universe that obscures light behind it. There are also things that you can't see through in the universe. Say, the same big beautiful galaxy is keeping us from seeing anything that might be behind it. I work in a field called multi-messenger astronomy, which is trying to figure out ways to look at the universe that don't use light. In particular, I study something called gravitational waves, and we think that these will help us find out things about the universe that are wonderful and weird and could tell us so much about how physics works at a basic level. Things like the inside of black holes, or what happens when a sphere of matter gets so dense that everything gets pressed into neutrons, or what happens when a star collapses and explodes and makes a supernova so bright that it's as bright as the entire galaxy it's in. I find it wonderful and amazing that we're trying to use this force that we see all the time, gravity, to figure out all these things about the universe. To talk about gravitational waves and how they work, let's just go back and talk about gravity for a minute. You might recognize these two men. Isaac Newton came up with the first theory of gravity. He described gravity as the force between two masses. This is a pretty good model. It was a model that started the idea of modern physics, something where we can describe things in the world and in the universe using mathematics. It works great for explaining why it's harder to go up the stairs instead of down, and why things fall down instead of up. But it doesn't quite tell the whole story. In the early 20th century, Albert Einstein changed a lot of things about physics, and one of the things he changed was how we think about gravity, space, and time. For Newton, space and time only existed in that there are objects and events that in the universe and in the world that happen, and you have to have a way of describing their order and their location. The difference between Newton's idea and Einstein's idea is that Einstein thinks that space and time are real things and they interact with objects. We say that in general relativity, mass causes space-time to curve around it. And this ends up looking a lot like what we experience is gravity. So let me just draw that for you. Now, if we have a flat table, I'm just going to draw a little grid here for you, and we roll a ball on it, it will roll in a straight line. This is something you probably observe very frequently if you play marbles. Now say instead we have, instead of a table, a trampoline. And this trampoline, because we do these things in physics, we're going to put a bowling ball on this trampoline. And this will cause the elastic fabric of the trampoline to curve around the bowling ball. Now, you may have heard at some point a physicist talk about the fabric of space-time. It's kind of an interesting way to talk about it because it really does look like fabric. Now, of course, it's hard to make a 3D piece of fabric that stretches, so we think about this in 2 dimensions with just a flat piece of fabric. But if we took this same marble here, it's going to curve around the bowling ball. And if you get the angle right, it'll start orbiting it. And this is how you can get a gravitational force out of curved space. Now, you might wonder, is there an actual difference between this model where there are two masses being pulled together and the model where time and space curve around mass and therefore gravity happens? There is a small difference. Otherwise, we wouldn't keep dealing with things in this much more complicated curvature model. And there actually is a difference that matters to you. Up until recently, there wouldn't have been one, but then suddenly we all got GPS systems on our phones. Without taking into account that there is a difference in this model of gravity, you wouldn't really be able to get an accurate GPS reading from the satellite that is applying your information to the phone. Now, there's another interesting thing that happens in general relativity, and if you look at it, it says that space and time can support waves. This is what this would look like. If we took a set of beach balls and put them in a circle in the middle of nowhere, in the middle of space where there's nothing else pulling on them, and we let a gravitational wave go past them, it's going to change the relationships between them because it will make length longer in one direction and shorter in another, like pulling an elastic. And this is what this looks like. So as this wave passes, it'll change the relationship of length. Now this is kind of a weird idea, but we're pretty sure that this works this way because of an experiment done by two astronomers. Russell Hulse and James Taylor discovered a pair of binary pulsars, two neutron stars that orbit each other, something like this. They watched this rotation around each other, and they discovered that as time went on, they took this information for 8 years, they discovered they were getting closer to each other. They're getting closer to each other because they were losing energy. They lost most of their energy to radio waves, but there was some energy loss that couldn't be described by how much light was coming out of these neutron stars. They took very careful measurements, they made very careful models, and they figured out that the model of gravitational waves explains why they were losing their energy at that rate. Now, we haven't seen a gravitational wave directly. We've only seen its effect on systems like this. But if we could see them directly, we could use them for multi-messenger astronomy. The project I work for is called LIGO, the Laser Interferometric Gravitational Wave Observatory. It is a joint project of Caltech and MIT. There are two observatories. This one is LIGO Hanford Observatory in Hanford, Washington. And this one is LIGO Livingston Observatory in Livingston, Louisiana. Each of them has these two arms, which are 4 kilometers long, and contain in them metal tubes that can hold the world's largest and most perfect vacuum. In this vacuum, we propagate lasers, we make them measure the distance in the tube to figure out if gravitational waves are passing. This is what it looks like on the inside. I've simplified this quite a bit. There are many more mirrors that are essential to the operation, and several mirrors that are very important to the operation. But we can understand it using a very small subset of them. We start by taking a powerful laser, a 200-watt laser, and shooting it at a half-silvered mirror, a beam splitter. Because it's half-silvered, half the light reflects one way and half passes through. At the ends, there are more mirrors, and the light bounces off these mirrors and comes back. We've combined the light and put it into a detector, which asks the question of the lasers, how far did you travel? To explain how this can measure gravitational waves, let's say that instead of using a laser to measure it, we instead used 2 cars. If we asked these cars to drive down to the end stations and come back, and we look at the odometers, because it's 4 kilometers and they're doing that distance 2 times, we wouldn't be surprised if the odometer said they traveled 8 kilometers. But what if the other car said that it traveled 8.5 kilometers? These are identical cars. This isn't a problem with the odometer. What happens with gravitational waves is that sneakily, while this is happening, gravitational waves come along and dig a bunch of hills and valleys in the road. So to us, this looks perfectly straight, but to a laser, this looks like it could have a bunch of hills and valleys in it because of gravitational waves passing. It's a good thing we don't use cars, by the way. My trip odometer is accurate to 1/10 of a mile. A laser's trip odometer is accurate to within 1/100 of a thousandth of the width of a human hair. And it's a good thing that it's this accurate, because we're measuring something that's very, very small. Gravity is a very small force. In fact, every day you produce a force that is going to be stronger than gravity when you put your grocery list on the refrigerator with a cheap magnet. Because gravity is so weak, we need to look at really big things. And to get this accuracy, we're going to have to take something and measure something the size of a galaxy to accuracy of the width of a fingernail. And we're going to be measuring things that are as big as galaxies. We'll be measuring, the effect of a supernova within a galaxy. We'll be measuring neutron stars, black holes, things that are some of the biggest and most extreme things in the universe. So gravitational waves, because we can only look at things that are produced by very large objects, falls into the realm of multi-messenger astronomy. Now, unlike most astronomy, we don't have to point at what we're looking at. We don't take LIGO and, like a telescope, look at this galaxy while being unable to see what's right behind us. LIGO acts more like an antenna, and I can explain that in terms of everyone's favorite antenna, a radio. Your radio is always picking up radio stations at all the times, putting out information in the form of radio waves. In the same way, there are many objects out in the universe putting out gravitational waves. Also, like a radio, you don't walk around hearing the latest hit songs in your head without a radio to turn them from radio waves to sound. For us, we need LIGO to turn things from gravitational waves to things we can actually measure. Also, like a radio, if we just turn it on, it's just going to sound terrible. With a radio, you have to figure out where the signal is you want to look for among all the other radio signals out there. With LIGO, our problem is not that there are too many gravitational signals, but that there's too many signals that keep us from seeing gravitational signals. These signals are as big as earthquakes or as small as wire moving against glass. So how we deal with this is, first, we try and reduce these noise sources, but secondly, we tune in. Just like you tune in to your favorite radio station, we tune to a certain signal using computer programs to find gravitational waves. Over the past 3 years, I've been working to install the next version of LIGO, the Advanced LIGO project. This involves upgrading almost everything in the observatory to make it more sensitive and easier to find gravitational waves, so we can finally detect gravitational waves. We can join in this multi-messenger astronomy community. We can find what happens inside a black hole, how a supernova happens, what happens to matter when you compress it down to a neutron star, and maybe even get a peek at the beginning of the universe. If you'd like to find out more about LIGO, you can find us at ligo.org, ligo.org.